Welcome to section 9.6. So this is our final section that we're covering from chapter 9 in solving these systems of differential equations. Up until this point, we have been exclusively working with the homogeneous systems of differential equations. Those are the form x prime equals ax with no additional plus b term. Today, in this section, we're going to be looking at solving the non-homogeneous linear systems. So that is x prime equals ax plus b, where b is non-zero. The system that we have for solving something like this incorporates the work we have done the whole chapter and a new step. So we're going to first, for step 1, solve the corresponding homogeneous system for our complementary solution. And then we're going to find one particular solution for step 2 to that non-homogeneous version. And then our final answer is, of course, the complementary plus the particular, just like we saw back in chapter 8 as well, when we were solving single differential equations. So the complementary solution, this is basically what we've been working on up until this point in the chapter. So it's just c1x1 plus c2x2 plus yada, 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 all the way up through cnxn. If we break that apart into a product of a matrix with a vector, so we have this matrix right here with x1 through xn in the columns of this matrix times this vector of c terms, c1 through cn. This matrix here, if we recall, is the fundamental matrix. That was abbreviated, so capital X of t. So notationally, the complementary solution is x of t times c, where c is that vector with all of those coefficients in it. Our particular solution is going to have the form x of t times u of t, where u of t is equal to the integral of x inverse times b dt. Okay, where x inverse, of course, is the inverse of that fundamental matrix, and b is that non-homogeneous vector that we have in our form back up at the top. And we need to then integrate that product, whatever it produces, and that will give us our particular solution. And this is really the only new piece that comes in from this. Our complementary solution still utilizes the same work that we saw in the previous sections. So let's take a look at an example of this. So find the general solution to x prime equals this 2 by 2 coefficient matrix A, which is 2, -1, -1, 2 times x, plus this vector 0 for e to the t. So we're going to start with step 1. We need to identify eigenvalues and eigenvectors to get that complementary solution. So we have determinant, we have 2 minus lambda, -1, -1, and 2 minus lambda. So that gives us 2 minus lambda squared minus 1, which expands out to lambda squared minus 4 lambda plus 3 equals 0. Okay, this whole thing equal to 0. That does factor lambda minus 3, lambda minus 1. So we get lambda is 3 and 1. So we're not going to go through the whole process here, but if you're looking for extra practice of those topics from the last few sections, then by all means try this one out on your own as well. But we'll get, for the eigenvalue of 3, we get eigenvector -1, 1. And for the eigenvalue of 1, we get corresponding eigenvector 1, 1. So that gives us our complementary solution. That is the solution to the corresponding homogeneous system. So that's just this part. So that's going to be C1 e to the 3t negative 1, 1 plus C2 e to the t 1, 1. So that's our complementary. Now, for step 2, we need to find our particular solution. So xp. So that's going to be the fundamental matrix X times U. And this is, of course, where U is the integral of X inverse times B. So we need to first get the fundamental matrix that we can then invert. So X of t, that's going to be negative e to the 3t and e to the 3t and e to the t and e to the t. Okay, right? Because we get that and that. So that's our x1, that's our x2. From here, in order to get its inverse, because this is a 2 by 2, getting its determinant can actually help us in finding its inverse. So the determinant of x of t, in this case, if we do the cross multiplication here, we get negative 2e to the 4t. So our inverse, so we're throwing it way back to chapter 2, when we first learned about how to find the inverse. We take 1 over the determinant, so 1 over 2e to the 4t. And we're going to flip the a and d terms, and we're going to negate the b and c terms. So that's e to the t, negative e to the t, negative e to the 3t, and negative e to the 3t. I'll leave the negative 1/2 out here in the front, but if we bring in e to the 4t, we can kind of simplify this a little bit. So this is 1 over e to the 4t. So that's going to turn this into e to the negative 3t, negative e to the negative 3t, negative e to the t, and negative e to the t. To the negative t. Negative on both of those. All right, just divide e to the 4t under each of these terms, and we end up getting, just subtract the 4t from whatever power was already there. So for our u of t, we need the integral of x inverse times b. There's a negative 1/2 here. I'm just going to pull that out to the front to begin with. So we get integral of e to the negative 3t, negative e to the negative 3t, negative e to the negative t, and negative e to the negative t, times our matrix B from back up here at the beginning of the problem. That's 0 and 4e to the t. So 0 and 4e to the t dt. So negative 1/2 is still there. We multiply these together, so we get 0 and negative 4e to the negative 2t when you combine those exponents. So negative 4e to the negative 2t. And then 0 and negative 4e to the 0. So that's just negative 4 dt. We can go ahead and multiply the negative 1/2 back in now. I think that'll kind of simplify things a little bit. So that would give us just 2e to the negative 2t and 2 dt. And now we integrate with respect to t. So we're undoing kind of a chain rule right here. So that's negative e to the negative 2t. And this one will just give us a 2t. So that's u. And our particular solution is the fundamental matrix times u. So fundamental matrix, of course, was this one. So we're going to perform that multiplication here. So our particular solution, so we have negative e to the 3t, e to the t, e to the 3t, e to the t, times negative e to the negative 2t and 2t. And this is going to give us a 2 by 1. So we combine those, we end up getting, so e to the t plus 2t e to the t. Same thing for second row with that column. We get negative e to the t plus 2t e to the t. And that is our particular solution for this system of differential equations. So our final general solution is going to consist of the complementary. So that was the solution to the corresponding homogeneous piece. And now we find one particular solution for the non-homogeneous piece, and that's this one. So now we just combine together. So we get x of t equals c1 e to the 3t times negative 1, 1 plus c2 e to the t times 1, 1 plus all of this and that would be our general solution to that system of differential equations, which of course now this gives us the tool to be able to solve non-homogeneous linear systems of differential equations. And that is really the only new piece that we have for this section. So that's going to bring us to the end of section 9.6. And that is the end of our journey through this chapter and through our introduction into the exploration of solving differential equations and systems of differential equations using the tools of linear algebra.